In this demonstration, we're going to take a look at how we can use StarDrop to prioritise and select compounds. The results of a high-throughput screen have been loaded into StarDrop in a column labelled pKi. There are just over 850 compounds in this dataset, and we can use StarDrop's ADME and physicochemical models results alongside the experimental data to identify high-quality compounds. Having run all the models, the dataset now contains over 15,000 data points, which presents us with a multi-parameter optimization challenge. However, in StarDrop we can define scoring profiles that indicate all the properties we're interested in optimizing, along with their relative importances. These enable us to score compounds to identify those which have the best overall balance of properties. Scoring profiles can easily be created, edited, and saved for future use, and in this example we have defined a scoring profile for a potent, orally bioavailable CNS target. Having scored the compounds, we can see that this compound has a relatively high chance of success, whereas this one does not look so favourable due to a poor balance of properties, as indicated by the multiple low bars in the scoring histogram. Sorting by the score enables us to identify the best compounds in a set. However, we'd now like to relate these scores to the diversity of the chemistry in this screening collection to identify hotspots in the chemical space which have good potential. StarDrop's chemical space visualization enables you to see your compounds represented in terms of their chemical diversity. Compounds which are close together have similar chemical structures, whereas those further apart are more diverse. Any selections made in StarDrop's visualizations are dynamically linked to the dataset and vice versa, so that you can easily keep track of compounds. In this case, we're going to color the chemical space based upon the scores, so that we can see which areas of the space contain the most promising compounds. We can also create multiple plots simultaneously by detaching one or more copies of the visualization window, and, again, all selections made in the plots are linked to each other and the dataset. Selecting this low scoring region of the chemical space reveals that the compounds therein generally have high log P values, whereas this hotspot contains compounds with a much better range of log P. If we look at a snake plot, we can see all of the compounds ordered by their scores. The error bars show us the effect of the combined uncertainties in the data we're using. One approach we could take is to simply select the 50 compounds with the highest scores. However, we can see that by doing this, there are regions of the chemical space which we would be ignoring, which wouldn't necessarily be the best approach for following up the primary screen. We can use StarDrop's selection tool to choose 50 compounds for us which cover a reasonable amount of the overall diversity, while still retaining a bias towards the top scoring compounds. We can see from the chemical space that the suggested selection now represents greater diversity, that there are only one or two clusters from which no compounds have been selected. At the same time, the snake plot shows us that we have still chosen a selection which is heavily biased towards compounds which have the best overall balance of properties. If you would like to try StarDrop for yourself, then please get in contact with us by email or through the website.